So, how do machines actually decide things? And I'm not talking about some crazy, complicated black box here, but something simple, something logical, something you can actually follow step by step. Today, we're going to pull back the curtain on one of the most powerful and yet intuitive models in all of machine learning, the decision tree.
All right, so check this out. On one side, you've got this super simple table of data, just info about when someone might play golf. And on the other, an intelligent flowchart that's basically learned from that data. The million-dollar question is, right? How do you get from A to B? How does a machine automatically turn that table into this smart decision-making tree? Well, that's exactly what we're going to unpack.
So let's get into the big idea here. And honestly, it's surprisingly simple. Just think of a flowchart, the kind you might draw on a whiteboard. Now imagine that flowchart could learn its own rules just by looking at a bunch of data. That's a decision tree.
Okay, so if we're going to get a little more technical for a second, a decision tree is what's called a supervised learning algorithm. All that means is that you have to give it data that's already labeled with the right answers. It learns from examples. What's really cool is it doesn't need a bunch of assumptions about your data. It just looks at the features you provide and figures out a series of simple, if this, then that rules, all on its own.
And this right here, this is probably one of its biggest selling points. We call a decision tree a white box model, and that's because you can literally lift the lid and see exactly how it's thinking. You can follow the logic from top to bottom. This is a massive deal compared to black box models, like, say, a deep neural network, where the internal logic can feel like a complete mystery. So, what's it made of? It's actually super simple. You've got the root node right at the top. That's where it all starts. Then you follow the branches down to these decision nodes. Think of these as the question askers. They're what split your data up. And finally, you get to the leaf nodes at the very bottom. These are the endpoints. They don't ask any more questions. They just give you the final answer, the prediction. Okay, so we've got the what. But now for the how. How does a tree actually put all these pieces together to make a prediction? Let's see it in action.
The process is basically a top-down sorting game. You start with your whole dataset in one big pile at the root node. Then the algorithm figures out the single best question it can ask to split that pile into smaller, cleaner piles. And it just keeps doing that over and over for each new pile. It asks another question, splits the data again, and so on, until it gets to a pile that's pure, where everything in it has the same outcome. Or, until it hits a limit you've set.
Let's go back to our golf example. So the algorithm looks at everything it knows, the outlook, the temperature, humidity, wind, and it has to make a choice. What's the best first question? In this case, it decides the smartest first move is to ask about the outlook. Boom. It splits all 14 examples into 3 branches: sunny, overcast, or rainy. And check this out. This is where the magic starts to happen. Look at that overcast branch. Every single time the outlook was overcast, all 4 times, the decision was yes, play golf. That group is perfectly pure. There's no uncertainty at all. So the algorithm knows its job is done right there. It slaps on a leaf node that says yes and moves on. But what about when it's sunny? That branch is still a mess, right? It's got a mix of both yes and no answers. It's not pure. The algorithm sees this and knows, okay, my work's not done here. It has to ask another question for just this group to try and sort it out even more. And that leads to the biggest question of all. Right, this is the real secret sauce, the part that makes it all work. How in the world does the tree know which question is the smartest one to ask? Why outlook first? Why not temperature or humidity? Because this is what makes a decision tree intelligent. It's not just guessing. It's not picking features at random. There's a method to the madness, a mathematical way it figures out the most powerful question to ask at every single step of the way. The whole thing comes down to one key concept: impurity. And really, impurity is just a fancy word for how mixed up a group is. Think about it. If a group has only one answer, all yeses, it's perfectly pure, 0 impurity. But if it's a 50-50 split of yes and no, that's as messy, as impure as you can get. So the algorithm's entire goal is simple: make splits that reduce that messiness, that impurity, as much as possible. Now, how do you measure this messiness? Well, there are 2 popular ways. You'll hear them a lot: Gini impurity and information gain. We are not going to get lost in the math formulas, don't worry. The only thing you need to remember is this: with Gini, a lower score is better. With information gain, a higher score is better. They're just two different tools for the same job, finding the question that creates the cleanest possible groups. Okay, let's make this super practical. Let's say we're trying to predict which students play cricket. We have two options for our first question. We could split the group by gender, or we could split them by class. Just by looking at it, which one seems to do a better job of separating the players from the non-players? Well, the tree doesn't guess. It's going to calculate the impurity for both options and tell us for sure. And once the math is done, the answer is clear. Splitting by gender gives us a Gini score of about 0.409. But splitting by class? That gives us a higher, more impure Gini score of 0.491. And remember what we said about Gini? Lower is better.
So there you have it. The split on gender is the clear winner. It gets the lower Gini score because it did a better job creating pure groups. And that's it. That's how the tree decides. The algorithm picks gender as the best question to ask here. And then it does this exact same calculation at every single node all the way down the tree.
So decision trees sound pretty awesome, right? They're simple, they make sense, they're powerful. But like any tool in the toolbox, they're not perfect. They've got their good sides and their bad sides. So let's do a little reality check.
Okay, on the plus side, they're super easy to understand and visualize. That whole white box thing. You also don't have to kill yourself with a ton of data prep, which is nice, and they handle all kinds of data without any fuss. But on the downside, they have a nasty habit of overfitting, which means they can get way too complicated. They can also be a bit unstable. Even tiny changes in your data can sometimes create a totally different tree. And they can get biased if your data isn't balanced.
Let's really dig into that biggest problem, which is called overfitting. This is when the tree basically learns the training data too well. It starts memorizing all the little random details and noise instead of learning the actual general patterns. It's like a student who memorizes the answers to a practice test but doesn't actually understand the subject, so they fail the real exam. A tree that overfits will look great on the data it trained on, but it will be terrible at making predictions on new, unseen data.
So how do we stop this from happening? Well, we have a few tricks up our sleeve. One is called pruning, where we literally just snip off branches of the tree that aren't very useful. We can also just tell the tree to stop growing after it reaches a certain depth. Or we can set a rule that says every final leaf has to be based on, say, at least 10 examples, so it can't make a decision based on just one weird outlier.
Okay, enough theory. We've talked about how they work, the good and the bad. But where do you actually see these things out in the wild? Where's the real-world payoff? Honestly, they're kinda everywhere once you start looking. Banks use them to decide on loan applications. And because they're a white box, they can actually explain why a loan was denied. In healthcare, they can model diagnostic pathways for doctors. Businesses use them all the time to predict which customers are likely to leave. Even in finance for fraud detection. The list just goes on and on.
And that really brings us to a final interesting thought. We live in a world where AI is getting more and more powerful, but also more and more like a black box that we can't understand. So in an age like that, does a simple, transparent model that you can actually explain to someone, does that make the humble decision tree more valuable than ever before? Something to think about.